Minerals are the building blocks of the Earth, but did you know that minerals themselves are commonly made of shared building blocks? We can visualize the crystal structures of these minerals using a series of 3D printed building blocks called TotBlocks. In this video, we'll take a look at the Kaolinite-Serpentine group.
The name kaolinite comes from the French pronunciation of Gaoling, a village in Jingdezhen City, Jiangxi Province, China, also known as the porcelain capital of China. Serpentine, on the other hand, means serpent rock, in allusion to its green color. It goes without saying that the most famous use for kaolinite is in porcelain pots and vessels, whereas serpentine has been used in rock carving. The Kaolinite-Serpentine group is also known as the 1-to-1 phyllosilicates because their structures consist of one T and one O module. Here's the structure of lizardite, which consists of infinite sheets of TO layer modules. Now, let's take apart its structure so that we can reassemble it. And you can use a straight edge to take apart the modules. To construct the lizardite structure, vertically join double chain with T+ modules to O+ modules. These TO modules can then be joined widthwise so that there is no vertical offset between the connected modules, which illustrated the sheeted nature of the structure. Missing sites in the O layer can be filled using single octahedron pieces. To vertically stack the sheets, pegs are inserted into the slots of the O layers. As an added note, there are two parts or two sides of the pegs. There is a triangular end and a hexagonal end. And the triangular end goes into the bottom of the sheets, or the bottom sheet. For the Kaolinite-Serpentine group, silicon will fit into the T sites, and aluminum and magnesium, for example, will fit into the octahedral sites. The crystal structure of the Kaolinite-Serpentine group is distinct among all of the other modular silicate minerals. Most modular silicate minerals have a TOT structure, but the Kaolinite-Serpentine group only has TO modules, which do not have the top T modules. As it turns out, the symmetry of having two T modules sandwiching both the tops and bottoms of the O modules is important. This is because the T and O modules are not always exactly the right size, but having TOT modules stops the size mismatch from getting out of control. On the other hand, the TO modules do not have that same symmetry, so the size mismatches can lead to the bending of the TO modules. These mismatches can be solved in different ways, leading to the existence of polymorphs, or minerals that have the same chemical formula but different crystal structure. In lizardite, there is conveniently no size mismatch, so the TO modules can extend to form infinite sheets. This makes lizardite take on a platy habit. In the structure of crystal teal, however, the O modules are slightly larger than the T modules, causing the modules to bend. The modules bend in on themselves like a curled up piece of paper. This makes crystal teal take up a fibrous appearance, which is also known as an asbestiform habit. Antigrite also has this size mismatch problem, but it solves the problem in a clever way. The modules flip-flop so that the bending is effectively cancelled out. The modules are modulated lengthwise using T+, T- bonds, while maintaining a continuous octahedral sheet. This leads to antigrite developing a platy, striated habit. In this video, we've looked at the crystal structure of the Kaolinite-Serpentine group, and we've constructed the structure of lizardite, one of the three serpentine polymorphs. We've also looked deeper into the unique TO configuration of these minerals, which leads to structural deformations in their modules and the development of polymorphs.